Welcome to lesson 43, Mass Energy and Binding Energy. Here's the plan for today. The equation is famous, but the meaning matters. Mass and energy are interchangeable. They are two forms of the same thing, and c squared is the exchange rate between them. It comes out of special relativity, the idea that we trade moving quickly through space for moving more slowly through time, with c, the speed of light, as the universe's speed limit tying it all together. And we've actually seen it already. The sun loses mass as it shines, annihilation converts mass entirely into energy, and pair production does the reverse, both from lesson 2. This is the equation behind all of it. Now the units, and this is a place where people get confused. We can measure nuclear masses in atomic mass units U, where U is 1/12 of a carbon-12 atom, which is roughly the mass of a proton. And you'll see it stated that 1 U equals about 931.5 mega electron volts, MeV. Now hang on, U is a mass and MeV is an energy. How can they be equal? Because the c squared is actually hidden inside the conversion. They've done the multiplying for you already, so that number is really saying 1 U of mass converted via E equals mc squared releases 931.5 mega electron volts of energy. It's a convenience, and it saves you a step. So how do the questions work? They'll give you every exact mass but one. 3 steps. 1. Write out the left-hand side and the right-hand side of the equation, remembering to include the energy released as one of the terms. 2. Sum both sides and find the unknown by subtraction. 3. Convert to MeV if they ask for it. It's careful bookkeeping and nothing more. Now back to our puzzle. Put a proton on the scales, mass 1. A neutron, mass 1. So a nucleus of 10 nucleons should read 10, but weigh it and it reads about 9.86. Mass has vanished. Here's where it went. Picture the nucleus sitting apart, separate and unbound. Now let the strong nuclear force pull them together. As they snap together, energy is released, just as a ball rolling into a valley releases energy. And by E equals mc squared, that released energy has to come from somewhere. It came from the mass. So the bound nucleus genuinely weighs less than its separate parts, because some of the mass was radiated away as energy when it formed. I like the funnel picture. Pull the nucleons apart and they're just ordinary nucleons with their ordinary masses. Squeeze them together, bind them, and energy, which is to say mass, comes out. So the total bound weighs less. So the mass defect is the difference, the summed mass of the separate nucleons minus the actual mass of the nucleus. And the binding energy is just the mass defect times c squared. And read the binding energy the right way round. It is the energy you would have to put in to rip the nucleus completely apart, back into separate nucleons. A big binding energy means a tightly bound, stable nucleus. Now we can consider the binding energy per nucleon, which is just normalizing the binding energy by the number of particles in the nucleus. We compare that against the nucleon number A, and we see the following graph. The lighter elements, up to iron, have a very steep gradient, which means the binding energy decreases very quickly. At iron, the binding energy plateaus, so it's the lowest that it can be. This is where they are the most stable. And as the nucleon number increases up to the heavier elements, there is a steady increase in the graph. But we need to think about what this actually means, and I've put these small blocks over the graph to visualize it. So think of one of these columns as being a measuring cylinder, and we pour water into it to let a little ping pong ball float up to the top. That ping pong ball is the nucleon, and filling up the measuring cylinder with water is like giving it energy into the nucleus. Here's the key point. The ping pong balls that are higher up, i.e. very light nuclei, have ping pong balls that are already very close to the top, so you only have to put in a small amount of energy, 1 or 2 blocks of water, to release it. Then, iron is the most stable, so you'll have to put the most amount of water or energy into it to release the nucleon. This is really important because the binding energy is actually a deficit. It's a negative number, like how we measured the energy levels as being negative for the nucleus. And it's really important when we think about the energy that is released in fission versus fusion, both sides of the graph. In the top right of the screen, we can see the graph upside down, which they'll sometimes put because they like the binding energy to be the absolute value, i.e. all positive numbers. So just be careful with that. And that's the end of the video. Thanks so much for watching, and check out my tutoring page below.